Okay, we are back. I hope you guys enjoyed your summers. Now we're back in the full swing of things, and we are going to take a look at force. Really, this is mostly a review from last year, maybe using a couple different techniques that we haven't used in the past. But for the most part, this is all review from stuff that we've done previously. As far as what force is a push or a pull, and you guys have a pretty good sense of what a force is. And really what we do is look at how a force acts on a mass. So, and again, a mass is a resistance to a force. We don't really look at it as the amount of stuff like a chemist does. Chemists like to look at the amount of stuff because they want to make sure that the amount of stuff that they have at the beginning is the amount of stuff that they have at the end. So that's why chemists talk about the amount of stuff. Physicists, we don't really care about, well, we do care about stuff, but we're more concerned about how it reacts to a force. And the more mass you have, the more resistance it's going to apply to a force, okay, or the less it's going to accelerate. So now, from that, we're going to talk about 3 laws of Newton. For the SAT 2, this might be helpful, not for any test in here or for the AP test. But we're going to name off Newton's 3 laws. I'm not big into memorization, but it is useful for some standardized tests when you're looking at when you look at SAT 2. So now, Newton's first law. Okay. What this says, pretty simply, is that a force, if no net force is acting on an object, okay, if no net force is acting on an object, the object will not accelerate. It will move with a constant velocity. That is most easily seen by something that doesn't move. So right now, there is no net force acting on this object, so it doesn't move. It doesn't have to be still. Okay? Right now, I'm going to walk across here like this. There's no net force acting on this because it's moving with a constant velocity. You could be moving pretty fast with a constant velocity. Okay? When I go like this, okay, that's a constant velocity. There is no net force acting on it. If I drop it, okay, there is a net force acting on it. That's really what Newton's second law says. So Newton's first law basically says that if the sum of all forces equals 0, okay, then delta V as a vector, and force is a vector, then delta V also equals 0. Okay. Different examples that you see of this. Specifically in physics class, when we talk about statics, and we did all those statics problems last year, that is an example of Newton's first law. When the famous shot of the person who pulls out the tablecloth and doesn't move any of the knives or forks or place settings or anything else like that, that's Newton's first law as well. Okay. And we don't really focus on that too much outside of some of the statics problems. Newton's second law is really where we're more interested. And this is where all the problems lie. The sum of all forces is equal to mass times acceleration. And yeah. So now, what the first law says is that if there is no force, no net force, there is no acceleration. What Newton's second law does is say if there is a net force, how that affects mass. Okay? So the net force is equal to mass times acceleration. I'm not going to get into the history or anything else like that. But Newton was more, he talked about it in terms of momentum, that if there's a net force, it will change an object's momentum, or what he called quantity of force. But how we use this is like that. Okay? And we're going to get into all sorts of problem solving and everything else like that. But from a SAT 2 standpoint, that's what that says. All the problems that we're going to do pretty much in this chapter are based off that. I'm not going to get into it too much because we really have to just get into a problem to understand how that works. Along with that, we have the gravitational force. Okay, just kind of naming off some forces here and how we describe them. We have gravitational force. Sometimes it'll be like this. Other times you'll see it as mg. Okay, which is mass times acceleration due to gravity. Again, these are all forces. Also, weight is the gravitational force. So, if you want to know your weight, it is the force of gravity that's acting on you. Okay. Now, let's see if there's one that I was missing. All right, then we also have stuff like the normal force, which I designate Fn. Other people will call it N. Okay, the normal force is the force that a surface applies to a mass, and it's the component that always acts perpendicularly to the surface. Along with that, we have friction. Okay? And we talked about it last year, kinetic friction and static friction. Static friction is what you have when the two surfaces are not sliding over top of one another. Kinetic friction is what you have when they are sliding over one another. Last year I said when it was moving and when it was not moving. That wasn't technically correct. Okay? It has to be that the two surfaces are sliding past one another. And we are going to get into lots of problems, especially when we get into rolling, where my original definition from last year doesn't hold up. And then we also, and by the way, this is the force that a surface applies to a mass along its length. Okay? We also have tension, okay? Which I usually use with capital T. Sometimes I'll call it A, for string A and string B, I'll call it A and B. But those are the different forces that we typically talk about. Okay? And we'll do a couple problems to show how that works. Finally, we have Newton's third law. Okay, what Newton's third law is telling us is that for every force, and by the way, these are all forces, for every one force, there's an equal and opposite reaction force. I'll call that F1 prime. Okay? So there is some other force that acts in the opposite direction. In other words, okay, as I hold up this stapler, okay, I'm applying a force up on the stapler. The stapler is pushing down on my hand. Along with that, gravity is pulling down, okay, and the forces don't have to be in contact with one another. Gravity is pulling down on this stapler. The stapler is pulling up on the earth with its gravity, okay, with the stapler's gravity. Now, those two forces have to be equal and they're in opposite directions. Okay? Now, you might say, well, how does the stapler provide the same gravitational force as the Earth? Well, the key is that even though they're the same force, the mass of the Earth is so much more than the stapler here, okay, that the Earth doesn't notice, really, in any discernible way, but the stapler obviously does. Okay? Now, I'll put some of the sample problems. I'll just do that in this section as opposed to putting it into another section. So let's talk about some things with tension first. Friction, we're really going to hold off on, and the frictional forces we're going to hold off on until we get to the next chapter. Normal force as well, because really normal force, I'll talk about it a little bit, but normal force, we're more concerned about how it deals with friction as well. But, all right, so now when we do a problem, and the first problem I'm going to do, this is from number 45 in your book. Okay, and I can't believe I didn't give you number 49. So this is number 45 in your book. Actually, I'm going to give you number 40. As well. I love the monkey. All right, so now what I have are three masses with three tensions. All right, we've got mass here, mass here, mass here, and I'm going to pull with a certain force. Now, this is M1, M2, M3, tension 1, tension 2, tension 3. Okay. So now, they're going to be pulled over to the right. I know tension 3 is 65 newtons. That's given in the problem. Now M1 is 12 kilograms. 12 by 4, 31. So M1, M2, and M3. What it asks for in this problem, the magnitude, it asks for the magnitude of the acceleration. It doesn't ask for it as a vector. It's going to be right. It asks for T1 and T2. Now, a few things that we want to do. We want to set up, we want to draw the forces that are acting on these masses. All right? So now, if I do that, okay, it's a free body diagram. Now, I'm going to include the normal force in this, but we're assuming no friction. So now, if I do that, I've got M1 here, and I've got M1G going down, that's the weight, and I've got the normal force going up. I also have T1 that pulls in this direction. Okay. Similarly, I've got M2 here. That's got normal force 2 going up, and I've got M2G going down, and I've got T2 pulling in this direction. T1, this is this is an example of Newton's third law. Okay, T1 pulls to the right, pulls to the left over here. Same idea with mass 3. I've got my normal force goes up, I've got gravity, 3G goes down. Okay? T2 is pulling back, same in this direction. T3 pulling in that direction. Now, that's the full free body diagram. There are cases, situations, this one in particular, where it's good because it's good to look at this as one big massive system. So if that's one big massive system, you could write it as this, right? And all we would do is treat T1 and T2 as internal forces, okay? Because to the whole system, T1s cancel out, the T2s cancel out. So as one big massive system, I've got T3 that pulls to the right. I've got normal force 1 plus normal force 2 plus normal force 3. These cancel each other out. I've got M1 plus M2 plus M3 going down. This whole system is M1 plus M2 plus M3. times g. Okay? So these two cancel each other out. So if I did sum of all forces, and I'm going to specifically say in the x direction, that will equal mass times acceleration in the x, going back to Newton's second law. Right? If you didn't take the class last year, I'm going kind of quick. This is a lot of stuff that was covered last year. These two forces in the y direction, they cancel each other out. Okay? So there is no acceleration in the y direction. This would be an example of Newton's first law. Newton's second law, that's happening in the x direction. And because force is a vector, we can break it down into its components. So now, sum of all forces in the x equals mass times acceleration in the x. There's only one force that acts in the x direction, it's T3. The mass in the x direction is going to be, well, the mass in general doesn't have direction. It's m1 plus m2 plus m3 times acceleration. We know T3. We know M1, M2, and M3. All we have to do is solve for the acceleration. All right? So now T3 is equal to 65 newtons. M1 plus M2 plus M3, that's 36. That's 67 kilograms times A. So my acceleration in this case, okay, so that's 65 newtons is equal to 67 kilograms times A. So my acceleration in this case will equal 65 divided by 67. It's this one. .97 meters per second squared. Now, we actually did do a couple problems like this last year. Okay, this should be fairly familiar to you. Okay, I want to kind of fire up some of those neurons and synapses that I introduced last year. Okay, but now we want to solve for. Now we want to get T1 and T2. T1 and T2 are internal forces when you're talking about the large mass. We don't care about internal forces when we're looking at the whole system. Okay? So now, if we're going to find T1 and T2, we can't look at it as a whole system. We have to look at it as we have to isolate these into their own. So now I'm going to isolate M1. The reason why I want to isolate M1 is that it only has one horizontal force acting on it. Okay? M2's got these two, so if I don't have to, I'm going to try not to do this. I'm going to have to, but eventually. But I can get T1 by itself. There will only be one unknown. So now, I don't need the original picture anymore, because I already, the free body diagram is more descriptive. So now, in the y direction, and I'll write this out, the sum of all forces in the y direction equals 0. Okay? Normal force, M1g, they cancel out. I can solve for what the normal, I might as well just go ahead and do that. The normal force on 1 will equal M1, normal force on 1, that goes up, I'll make it positive. M1g goes down, so that's negative. This is all the sum of forces in the y direction. It's not moving in the y direction, so that's 0. So the normal force on 1 is equal to M1g. Okay? So that's going to be 12 kilograms times 9.8 meters per second squared. And so the normal force on 1 will equal 117.6 newtons. Okay? They didn't ask for that in this case, but it's just useful to know how to do, especially when we get into the next chapter. So now, we have solving for the tension on 1. So now, in the x direction, sum of all forces in the x is equal to mass times acceleration in the x. So I've got The only force acting in the x direction is T1. The mass is m1 times the acceleration. I know what the acceleration is. It's 0.97. 0.9701. Okay. So now, I solve for T1. I know that the m1 is equal to 12 kilograms. I plug in that 0.970 meters per second squared. And so T1 is equal to, I keep all the digits in my calculator, 11.64, I'll say 11.6 meters. Okay. Now I'm going to isolate M2. I can do M3 just as easily. There's no reason not to do M3. They have equal level difficulty at this point. So when I do that, I'm not going to go through the sum of all forces in the y. I'm just going to look at sum of all forces in the x. That equals mass times acceleration in the x. Okay, I don't need to know what the normal force is. So now, T2 pulls in what we, to the right, we typically make right, and the positive direction. It's also accelerating to the right, so it makes sense to do that too. So now, T1 pulled to the right on M1, but pulls to the left on M2. So now, I've got T2, so T1 has to be negative on M2. The mass is M2 times the acceleration. So now T2 is equal to M2A plus T1. Okay. I know that M2 is 24 kilograms, A is 0.97, and I know that T1 is equal to 11.64. All right, so now I plug in these numbers, and my value for T2 is equal to plus 34.9 joules. And when you guys do problems, please box your answers. It's just easier for me to see. Okay, well, that's about it. I'm also going to assign you guys homework on here. So with that in mind, all right, this is in chapter 5. There are 16 problems. They aren't due on Monday. They'll be due probably the following Monday or Friday. We'll talk about it. But we've got chapter 5. Okay, I've got 11, 18, 21, 24, 28. This is in the problem section. 35, 33, 41. 42. The monkey problem is 49. Always got to, whenever there's a monkey, you got to do a problem with a monkey. 49, 50, 52, 58, 67, 77, 82, and 95. Put those down in your notes so that you have the problems that we're going to be working on. I will lecture for a little bit. I'll go over this lecture with you guys if you have any questions. We're going to review for the test that we have on Wednesday for a little bit, and then I'm going to let you guys get on problems. This is a topic that you guys just have to do problems on. Any more lecturing, I don't think will be useful. So anyway, without further ado, I bid you adieu.